Binary trees 1. Today we're going to talk about binary tree, talk about an overview of binary trees, the things you need to know, the things you need to watch out for. And then after that, we'll go into our usual breakout sessions. And after that, we'll recap the breakout session and I will answer any lingering question afterwards. I'm also free to stay a little bit after lecture. So if you guys have any questions you want to ask me personally, or you can just ask with your fellow classmates, feel free to stick around after lecture. I'll be more than happy to chat. Also, I will stop looking at the Zoom chat. I will only monitor the Slack chat. So if you have any questions, if you see your classmates asking any questions in Zoom, please direct them to Slack. All right, so let's go ahead and get started. Let's talk about binary trees. It's actually one of my favorite data structures. I love asking these types of questions in interviews. So we're going to quickly go through some really basic stuff that you guys should already know because you guys have already done the warm-up, hopefully. So hopefully this should all be reviewed. So binary trees are comprised of nodes. Each node holds a value. Usually it's a string or a number. Pretty much most, if not all, the binary tree problems I've seen hold a string, character, or a number. And each node can have anywhere from 0 to 2 children inclusive. And a node with no children is obviously called a leaf. And a binary tree can have many different properties. It can have multiple properties. So it can be a BST, a binary search tree. It can be a balanced BST. It can be a complete tree, perfect tree, and all that stuff. We're going to talk about what each of those properties mean and what you need to know about them. Here's a basic binary tree node definition. This is usually the class that you're going to be mainly dealing with when you are answering binary tree questions. It's a very simple. You initialize a node with a value and you can explicitly assign the left and right children, right? This is all basic. You guys should already know this. In pretty much 80–90% of the time, this is how you're going to be messing with binary trees. Okay, things to know. Binary trees can look many different ways. So for example, a single node is considered a tree. You can have a tree where every level is completely filled except the last one. You can also have binary trees where every level is filled except for the last one, and all the nodes in the last level are to the left as far as possible. You can have a perfect binary tree where each node has 0 children or 2 children. And you can have this thing that looks like a linked list that's called a degenerate binary tree. And we're going to talk about why these cases matter. So in every binary tree problem, you are going to need to traverse it, period. It will require you to traverse it and sometimes manipulate the tree itself to the desired structure, right? Or, you know, if you want to remove values to it, add values to it or whatever, sometimes you're going to need to do that. Sometimes you're going to need to traverse the entire tree and get some value from it. And there's 2 main ways to traverse a tree. You can go through it in DFS manner or in breadth first manner, BFS. There's multiple ways to go about it if you want to go through it in a depth first manner. We're going to talk about that next. So you guys have already heard of in-order, pre-order, post-order traversals. You guys have probably done this in your algorithms class or data structure class in college. So let's just go through those. In order, all right? Whenever I interview candidates, some of them get this confused. They kind of mix up what in-order, pre-order, and post-order are. So here's the hints that I tell myself so that you don't forget what the ordering is for each of these traversals. In order. In order means left to right. So that means you process the left subtree, then you process the current node, then you process its right subtree, right? In order means left to right. That's the hint that I tell myself. Fun fact, if you traverse BST, a binary search tree, in an in-order manner, you get the sorted order. So let me show you, let me prove that to you guys, because this is a really cool thing I found while doing a lot of binary tree problems. So let's say, is my thing not, hold on one second. Hopefully this works. Come on, pen. Where is it? Please work, please work. Oh, yes, okay, good, it's working. Okay, let's do this. All right, so let's say I have 10 over here, I have 5, I have 15, 13, 18, 3, 7. So if I traverse this tree in an in-order manner, then I would start from here, then I would go to the left, then I would go here, then I would go to the left, here. This is a leaf, so I process it. So I get 3, I go back up, I process the current node, which is 5. Then I go to 5's right subtree, which is now 7. Then after that, I go back up, I process 10 now, then I go to the right, then I process 15 next. Then after that, I process 15's left child. Oh, sorry, I don't process 15. I process 13 because remember, it's left to right. So I process 13 first. Then I go back up to 15. Then I go to 18. So you guys can see, if I do an in-order traversal in a BST, I get the sorted order. It's a very useful thing to know when you're doing binary tree problems, especially if the thing you're dealing with is a binary search tree. Now, let me ask you this. If an in-order traversal gives you the sorted order of a binary search tree, how would you get the reverse sorted order? What type of traversal do you think you need to do? Anyone know? Or at least just tell me the ordering of which nodes to process first. All right, let's see. I got right node left. So if I process my right subtree first, then I process the current node, then I process the left subtree. What do I get? Okay, let's do that. So I'm starting here at 10. I process 10's right subtree first. Before I process 15, I process 15's right subtree. So 18 is going to be first. Then I go back up here. Now I process 15. Good. Then after I do that, I process 15's left subtree, which is 13. Then after that, I go back up here. I process 10 now. Then I process 10's left subtree. Before I process 5, I need to process 5's right subtree, which is 7. Then I go ahead and process 5. Then I go ahead and process 5 left subtree, which is just 3. So you guys can see, doing it that way will give you the reverse sorted order. That order is actually called reverse in order traversal. So the trick I like to tell myself is in order is left, current, right, and reverse in order is you just switch left and right. That's reverse in order traversal. Okay, that's the hint that I tell myself. So the reverse in order ordering will give you the reverse sorted order. Really useful thing to know when dealing with BSTs. Now, next traversal, pre-order traversal. Pre means before, right? That prefix means before. So that means you process the current node before you process the left and right subtree. Now, reverse pre-order simply means you switch the left and the right. So you process the current node, then you process the right node, then the left node. Post order. Post means after. So that means you process the left subtree, then the right subtree, then the current node. The current node is last. Post. Okay, after. Reverse post order. Again, you just switch the left and the right. So that means you process the right subtree, then you process the left subtree, then you process the current node. Any questions on these three traversals? Let me look in Slack. Let's see. Okay, what does hint for pre-order and post-order mean? I just explained that. Cool, someone posted what looks like an article. Thank you for that. applications for reverse post order. I can't think of one off the top of my head, but the key point here is that you need to be familiar and comfortable enough doing these different combinations of traversals. So you might be wondering, well, Mari, when I'm doing a binary tree problem, how can I know when I need to do a depth first traversal or a depth first search or whatever? What I would say is, one, there's no surefire way to know what traversal you need to do. It all comes with just experience and doing a lot of these types of problems. However, the thing to note is that how a problem is worded can give you clues in what the optimal solution is. So for example, keywords like max, deepest, longest, things that would suggest that you go down the binary tree as deep as you can are usually clues that you need some kind of depth first traversal. So for example, if I wanted to get the running sum of the path that I'm currently on up to the leaf, then chances are I probably need to do some type of depth traversal. Right? It makes sense because I need to first process the node that I'm currently at. And then after that, I need to process whatever values my children have. All right. So in that case, you probably want something like a pre-order traversal where you process the current node first, then you process your children. All right. So the thing with DFS is that you can implement it iteratively or recursively. At the very minimum, you need to be able to be very comfortable with doing pre, post, and in-order traversals. It's easy enough to do the reverse variants because all you need to do is switch the left and the right, right? So I know some of you guys are probably asking, well, Mari, should I implement it recursively or iteratively? My advice for that is be very comfortable with one way. But be somewhat familiar with the other way. So for me, I actually like to use recursion for binary tree problems because I found that a lot of problems that I encountered that are binary tree problems can be elegantly solved using recursion. I also find it harder to remember how to do things iteratively, especially if I wanted to do things like an iterative in order or post-order traversal. So it's mainly up to you what you feel most comfortable with, but be familiar enough to with the other way, just in case your interviewer pushes you to do it that way. So I have these 3 links. We're not going to do this because it's very rudimentary and it's very basic. You guys should already know how to do this, but these are just warm-up exercises for you guys, implementing in-order, pre-order, and post-order traversals. These should be muscle memory. You guys should not spend a lot of time in an interview implementing these types of traversals if you practice properly. Next thing, breadth first search / traversal. This is hopefully is review as well. Breadth first traversal is usually done using a level order traversal where you traverse the tree in a level order fashion. So for example, first you traverse the first level, then you traverse the second level, then you traverse the third level. Obviously, the level order traversal for this tree is A, B, C, D, E. Okay, level by level, left to right. Keywords. You will be surprised by how many problems you can spot if you just take a look at how a problem is worded. So if a problem has the keywords such as level, row, which, that's kind of a dead giveaway. If you want to get the level the values of each level of the binary tree, you probably need to do a level order traversal, right? If you want to get the minimum, for example, a breadth first, if you want to, let's say you want to get the minimum number of nodes from one node to the other, you probably want to do a breadth first search for that. If you want to get the width information of the tree or the diameter of the tree, or you probably want to do a breadth first traversal for that. Does order matter in level order traversal? So usually level order traversals go from left to right, then level by level. Obviously, you can do right to left, level by level. I don't know what the exact naming for that, but maybe yeah, I don't know what the name is for that type of traversal, but it's easy enough to do. It's easy enough to implement. Also, we'll also do a problem that is a reverse level order traversal, which is basically instead of going from top down, you go from bottom up. Let's see. How do I know when to use a DFS traversal and a BFS traversal? So one of the things, if you want to use a breadth first search, if you want to find the minimum path between two nodes, that's one thing. Again, I can't tell you all the different reasons of when you would want to use DFS versus BFS. You're going to have to just do a lot of problems to know which one is which. And also, sometimes it doesn't matter what kind of traversal you do, right? In some problems, it doesn't matter what kind of traversal you do as long as you visit every node. Is it possible to do level order traversal recursively? No, because if you were to do it recursively, the recursive function, the recursion call stack will act like a stack. And for a level order traversal, you need a queue. So I don't think there is a way to do it recursively. Is there a way to traverse starting from the bottom level first? If so, in what case should we use it? Yes, we will do that problem today. Let's see, Wenchi, you've kind of followed up. So Wenchi, I think in your example, the order does matter in your level order traversal. So there can be multiple level order traversals. You can either go from left to right, or you can go from right to left. So the orderings will differ. So in that case, it does matter. It also depends on the question, right? Maybe sometimes the ordering doesn't matter in the question. All right, let's go ahead and move on. All right, different properties of binary trees. All right, so there's going to be multiple properties of a binary tree. We're going to talk about the most common ones you should be aware of. The most common thing you need to know is whether or not a tree is balanced or non-balanced, and whether or not the tree is a binary search tree or a BST. Why does that matter? Because we'll talk about that in a bit. Also, other properties that are not as common, terms like full, perfect, complete, degenerate, binary tree. These are all things you might encounter when doing binary tree problems. You should be familiar with them. And again, thing to note, binary trees can have multiple properties. So you can have a balanced BST, a non-balanced BST, a complete BST, etc. And why this matters is tree properties are usually hints. So if you're reading a problem, if you're given a problem that has certain tree properties, those are hints in how you can get the optimal solution. So for example, if a problem is a BST, then you can probably bet on that the optimal solution is going to take advantage of the fact that the tree is a BST. Right? So make sure you read the problem carefully, because how a problem is worded are hints to how you can get the optimal solution. It's always good to ask your interviewer if a tree has any special properties. Sometimes they will flat out give it to you. Sometimes, it might not be as obvious, so you might want to ask them about it. So let's talk about balanced binary trees. A balanced binary tree is when the height of the left and right subtree of every node differs at most by 1. And what is height? Height is the maximum distance of any node from the root. So for example, this tree over here is balanced because the height of its left subtree is 2, and the height of its right subtree is 1. This tree is not balanced. The height of its left subtree is 1, the height of its right subtree is 3. So this tree is not balanced. Now, why does this matter? Because balanced and non-balanced trees impact the runtime complexity for trees, especially for binary search trees. So let me ask you guys this. Actually, let me ask you guys this. Why do you guys think that matters? If a binary search tree was not balanced, why do you think the performance will suffer? Can anyone give me an answer for that? Good, I see several people typing. Good. Unbalanced is O of n. Time complexity, let's see. The performance of a BST is no longer O of log n. That is correct. Good. So you guys already know what the disadvantages are. Good, good, good. Awesome. All right. So whenever you guys are making your test cases and analyzing the runtime and space complexity, make sure you are taking into account whether it's possible that you might have a non-balanced binary tree, because that will affect your runtime and space complexities. Next, BSTs. BST, that simply means the left subtree contains children that are less than or equals to the root. The right subtree contains children that are greater than the root. The great thing about BSTs is that it has better lookup and insert performance than non-BSTs. And the caveat is only if they are balanced. And as you guys said, if a binary search tree is not balanced, then it will have the same linear performance as non-BSTs. And again, the properties of a BST are usually needed to get the optimal solution. So when you guys are reading the problem and you guys see that something is BST, you are probably going to need to exploit the fact that it is a BST and make use of it in your algorithm to get the optimal solution. All right, cool properties of BSTs. A balanced BST has logarithmic performance for get, insert, and delete operations. You guys should already know that. Traversing a BST using an in-order traversal gets the ascending order. The reverse in-order traversal will get you the descending order. We already talked about that. This is the same, just similar to what I said earlier. Your time complexities will differ depending on whether the tree is a BST or not, and whether or not the tree is balanced or non-balanced. So if you look at this chart on the right, a non-balanced BST is all linear performance. Balanced BST is logarithmic performance. And again, remember your time and space complexities. A good interviewer will always ask you that, and always preface your assumptions. So for example, if this BST was balanced or non-balanced, then the runtime would be blah, right? Always preface your assumptions. Do not assume things, because if your interviewer does not have the same assumptions, then that will not look good on your, that you basically will not look good on that part, all right? So make sure you preface your assumptions. All right, perfect binary trees. This means every level is completely filled and every node has either 2 children or none. Okay, so a perfect binary tree is also balanced. Thing to know. A degenerate binary tree, if you want to sound cool to your classmates, you say a pathological tree. I remember in college, people were talking about pathological trees. I thought they were like the smartest people because it sounded so complicated. But honestly, all it is that it's a binary tree that looks like a linked list. Every node has at most 1 child. This is usually why your runtime and space complexity is linear for trees, especially for BSTs, right? So obviously a degenerate / pathological tree is a non-balanced tree. So you get the same linear performance for BSTs. And usually in a lot of cases, this is why your runtime complexity will not be as good, or if you use recursion, why your recursive call stack may reach as high as O of n. Okay, and this is because of this case over here. So actually, any questions before we dive into our problem walkthrough today? All right, if you guys have any questions, I will answer them after. Do we need to know about red or black trees, etc.? I don't think you need to know them by heart. They might be incorporated into certain into a few problems, but I believe they won't assume that you know what a red black tree is. You might, they'll probably, a problem will introduce to you what a red black tree is, and you will you'll know when you're solving something about red-black trees. But in my experience, I don't think it's a must, a thing you need to know. Really, the vast majority of binary tree problems that you're going to encounter has to do with these different types of traversals and just manipulating the tree. You don't need any prerequisite knowledge about red-black trees to solve most binary tree problems you're given, in my experience. All right. Any more questions? Oh man, we've gone for 42 minutes. Okay, we got till 6:45. All right, we got 17 minutes to do this problem. So we are gonna go through this problem, reverse level order traversal. Stop this, exit this now. We're gonna do this. So you can follow along over here. So given the root of a binary tree, return the bottom up level order traversal of its nodes values, i.e. from left to right, level by level, from leaf to root. So for example, given this tree over here, you're supposed to output a list of lists containing 15, 7, because 15 and 7 are the last level. Next is 9, 20, because 9, 20 is the second to the last level, and 3, because 3 is the root. Okay, pretty simple, right? Hopefully that's easy to understand. So what we're going to do is we are going to use umpire to solve this problem. So let's start with understand. This is a tree. I hate doing tree problems using text. I'm just going to draw them because it's much easier. So in an interview, you're going to be given probably one example, and it's going to be up to you to come up with the other test cases. So this is a gimme, right? This is going to be one of our test cases. I'm just going to put it over here. Test case 1 is going to be this. And the output for this would be 15, 7, 9, 20, and 3. All right. Test case 2. Can someone give me a good test case for this one? Anyone got any good test case? So this is like one of more of our happy pads kind of test cases. A degenerate tree. Yeah, that's a good test case. Let's go ahead and test a degenerate tree that looks like this, right? The output for this would be 7, 7, 20, and 3. Good. This is a nice test case. It's not too easy nor too hard. You guys might be wondering, well, what if we're passed in a null root? You know, sure, that could be valid. That's really easy to catch, though. You can just have an if statement and just catch it in 2 lines of code. So I don't like to do those for my test cases. I kind of just like to catch them when I start coding because it's easy enough to catch, you know? Let's see. Okay, we have an empty tree. Okay, we have a perfect tree. Let's go ahead and do that one. So this is a perfect tree. Yeah. All right. And then lastly, let's just make one more. What if there's only one node? Yep. Let's just do that. It's easy enough. Good. All right. So these 4 test cases, I think, are solid enough. They're not too easy. They're not too hard. So let's go ahead and move on to the next part. The next part is match and plan. CodePath explicitly kind of makes this into two steps. But for me personally, match and plan kind of go hand in hand. And you guys will realize this as you start using Umpire a lot, is that match and plan kind of just merge into one step. But for the purposes of this class, we're going to separate them out into two steps. So match is when we identify what kind of problem this is. Obviously, this is a binary tree problem. The easy thing about binary tree problems is that you usually know when you are solving a binary tree problem because you are given a binary tree, right? So the next step is plan. Plan is when we think of the patterns and techniques that we can use on this data structure or any previous problems we've done in the past to come up with an algorithm to solve the problem. So what are our different techniques that we can do in a binary tree? Well, we have different types of traversals. We have depth traversals. We have a breadth traversal, aka a level order traversal. So for depth traversal, we got our pre-order, in-order, and post-order. Do you guys think we need to do pre-order, in-order, or post-order traversal for getting the level order traversal of a tree? No, exactly. Look, you see how this problem is worded? Bottom up level order traversal, right? In a lot of these problems, you can get a good amount of clues just by reading the problem carefully. Of course, it says level order traversal. Why wouldn't you use a level order traversal for this problem, right? So just, merely reading it properly will give you a lot of clues in solving a problem. So don't just glance at a problem and think, and just, glance at the problem description, because the description usually has a lot of clues. So we're not probably going to need to do depth traversal. What we're going to need is we're going to need to use a level order traversal. And guess what? This level order traversal here is almost what we want. Level order traversal is going from top down. Here, we just need to reverse it. So once we get that, once we know that we almost can get what we need, all we need to do is do a level order traversal, and in the end, just reverse the resulting list. Now you can either store it in a list and just use the reverse API of your programming language for lists. But what if your interviewer says, oh, you can't use that reverse function? Can someone tell me, how can we solve this if you can't use the reverse function of the list? Stack, exactly. Good. So you can see now what we did is we've taken our knowledge of our previous data structures and applied it to this problem. If we can't reverse the list, we'll just put it on a stack and then just pop all those things in a stack in another list, which will yield to us the reverse order. Good. So our plan is to do a level order traversal and put the result in a stack. Pop all elements in the stack at the end and put them in a list. The result is the elements in the reverse level order. Good. That's all we need to do. We just need to do a level order traversal, keep track of each elements in the level. And at the end, we just need to reverse that list using a stack. All right, pretty simple. So now let's go ahead and code this up. So I'm going to use a double-ended queue. We're probably going to go a little bit over 45 minutes, which I think is hopefully it should be fine for you guys. Slightly less time in breakout rooms, but I think this is important to talk about. So can someone tell me, for you Python enthusiasts, why do you think I want to use a double-ended queue? Good. Let's see. You can pop from either direction. You can append left. You get, here's the key thing why I love it. You get constant performance in appending and popping from both sides of a queue, right? You get constant performance. Now, if I didn't use a double-ended queue and I just used a normal list and tried to use it as a queue, why wouldn't that be performant? Can someone tell me? So if I am popping from the left side of the queue using a list, if I want to pop the first element, we have to shift all the elements after that to the left ones, right? Popping the first element means we get linear performance because we need to move all the other elements to the left ones because we've removed the first element, right? In a double-ended queue, we don't get that, that performance cost. We get constant pops from both sides of the queue and also appends. So this is why I love double-ended queues. If you are using Java or any other programming language, make sure that the data structures you are using are performant. Okay. I haven't coded Java since college, so I wouldn't know what API to use, but you guys should know. So let's go ahead and use a double-ended queue here. Before, usually in the very beginning of a function, you usually want to check if the input is none or null. Again, this is why I don't like making an explicit test case for this because it's so easy to catch. So if root is none, then you just return an empty list. Okay, so here, what we're going to do is we're going to initialize a queue. We are going to start from the root, right? And we're also going to need a stack because this is what we will use to get the reverse ordering later. And what I'm going to do is I'm going to process this queue while there are elements in it. Okay. Now, you notice here, what I append to my queue is a list. It's a list of all the nodes at that level. In the first level, there is only one node, which is the root. So if I pop the queue, I get a list of nodes. So I'm going to call it nodes in level. It's going to be queue.pop left. I also want to take a note of what the results are for that level because we need to know that. And also we need to know what the next level of nodes are so that we can put that in our queue so that we can keep processing the tree. So now I'm going to go through each node for each node in nodes in level. And I'm basically going to put that in our next level list so that we can keep traversing down the tree. So for node in nodes in level, if node.left does not equal none, next level dot append node.left, right? We want to look at the left child first because we want to go from left to right. And I basically need to do the same thing for the right node. Okay. One thing here is that I also want to keep track of what the results are for the current level that I'm in. So I'm going to put this in result for level. I'm going to append the node's value. And once I do that, once I process all of the nodes at that level and I've put the all the next nodes in next level, I'm basically going to check if there are other nodes that are in the next level. So if len next level is greater than 0, then that means we need to put that onto the queue so that we can keep traversing the tree. All right. Also, I want to put the result for this level onto the stack. So I want to do stack.append result for level. And stack is going to be what we end up popping at the very end so that we can reverse the ordering of the levels. So once I've processed this entire tree, right, in this while loop, now I have a stack that is full. And all I need to do is reverse it, pop everything in the stack and put it in another list. So I'm going to have res is equal to list. And while len stack is greater than 0, res.append stack.pop. And in the end, I return res. All right. So it's 6:42 right now. So I'm just going to go ahead. We don't have time for the review portion, but what I would do in the review portion is obviously I would just go line by line, keep track of what the variable assignments are, and then make sure that it spits out the correct result. I would probably test out this happy path test case. And also I'll probably test one other test case over here that we came up with. And depending on how confident I feel, based on how my code performed in those test cases, I would say, okay, I think this is correct. Or if I wasn't yet confident, I would do more test cases to see if I can spot a bug or two. All right, so let me just go ahead and run this. We want to probably go ahead and do a breakout session soon. Let's see. Nodes in level is not defined. Oh. Cool. Let's run this one. Cool. Looks like that works fine. So let's see. Okay, let's see. Jin, I think, has a good point. Why do we need a stack as the auxiliary space? Why can't we just use a linked list as the output list and keep adding to the head along the way? You can do that. That actually makes things slightly more simple. That's valid. Yeah, I think what you can also probably do is just make this a another double end. Just append this, just do append left, I believe. I think you can just probably just do append left here. So you don't have to do that. But actually what you still need to do in the end is you still need an output list. So you still need to put this in a list somehow. So you're still gonna have to pop everything back to a list. In a virtual interview, what is the best way to write out these test cases, given it will be hard to draw out the trees? Yeah, that's a good question. Every company does things differently. Some companies give you a software so that you can draw stuff. Some companies also allow you to have a pen and paper in hand and just show it in the screen. I know it's a little janky, but some companies let you do that. Yeah. So it really depends on per company. For me, what I would do, whatever I'm most comfortable with doing it in pen and paper. It's really hard for me to say because this whole virtual interview thing is very new for everyone. But if I were you, I would probably have a pen and paper handy so I can just do things faster and just show it to the interviewer. What is the name of your drawing tool on Mac? What a great tool for virtual on-site virtual interviews. So I'm using the Zoom Annotate tool, but I actually have a tablet that I draw in, and I have a stylus. This is mainly for just me teaching a lot, but if you guys really want to invest in it, there are things that you can buy so that you can draw easily on the computer. Okay, so that's all I wanted to show you guys for our for our walkthrough problem. Now what we're gonna do is we're gonna go into breakout sessions, and you guys have 2 problems to solve. You guys have an hour to do it. You guys can either do it individually, then discuss with your pod, or you can do it by group, or you can do it together with your pod. It all depends on you. I'll give you guys free reign on what you guys want to do. You guys, I know some pods are more comfortable doing it individually. Some pods like to do it by a group. It really depends per pod. So I'm gonna give you guys that freedom to do whatever you guys want. But the goal is try to go through these 2 problems. I think you guys have enough time to go through 2 of them, to go through both of them, and then after that we're gonna finish up and do Q&A and stuff. All right. So everyone is back. Awesome. Okay, welcome back from breakout sessions. Let's just quickly go over 2 problems you were supposed to work on. First of all, min depth of binary tree. I think the main key thing I wanted you guys to see here is that sometimes it doesn't really matter what kind of traversal that you do. In this case, you could have done this with a depth first traversal or a breadth first traversal. Both have the same worst runtime complexity. However, on average, BFS will probably be better. So for example, here's the problem that you were supposed to do. So the worst case runtime complexity for this both would be for both depth first or breadth first would be worst case O of n, where n is the number of nodes. In this case, it might be on average be better for you to do a breadth first traversal in case one of the levels is very shallow and the other one is very deep. So for example, if you have a case like this, it probably might be better to do a breadth first traversal, because at least when you first encounter a leaf node, you know that is the most shallow leaf node. So you can just terminate from there and return the minimum depth. So that's the great thing about breadth first traversals, is that the first leaf node that you encounter will be the closest leaf node from the root. You could have also done this with depth first traversal, but on average, it might be worse because you might need to traverse a subtree that is much deeper than the leaf nodes subtree. Okay, so that was one problem. You could have done it either with breadth first or depth first traversal. Next one, binary tree pruning. So this one was a little bit more involved. I think the key thing here is figuring out what kind of traversal you need to do. So in this case, in order for you to prune a subtree, you first need to know whether that node contains a 0 and all of its children also contains a 0. So in order for you to determine if you can delete a subtree, you first need to traverse its children and then figure out if the root of that subtree is also a 0. So to do that, you need to do a post order traversal. Again, post means after. So you can only know whether you can prune a subtree after you have traversed the entirety of its subtree. So a post order traversal here would make sense. I personally did this myself using recursion, but you could have probably have also done this using the iterative version. It's up to you. But yeah, that was what I wanted you guys to get here, is figuring out what kind of traversal you need to do for this tree. And that's pretty much all the tree problems you're going to encounter, is figuring out what kind of traversal you need to do. Sometimes it doesn't matter, sometimes it matters. In this case, it mattered. You needed to do a post-order traversal. Let's see. Why is there a discrepancy between the concept of def defined in Stack Overflow, our article, and the LeetCode test cases? That's probably LeetCode's own definition of what depth means. What matters is that you apply the definition that the problem tells you to. So, you know, the definitions might differ. Like, for example, in this case, the definition of def differed. Sometimes that might happen for other problems. Just use the definition that is given to you, or ask the interviewer specifically what the definition for it is. Let's see. For the first problem, I used a global variable in my approach. Is it usually better to try and avoid global variables in our solutions for any problem in general? Yes, that's a good question. Yeah, you should. Avoid using global variables if you can. Sometimes if you just use global variables willy-nilly, that kind of is a red flag to the interviewer, meaning you don't really know how to structure your functions and your code properly. So if you can avoid using a global variable, please avoid it. If you absolutely have to, you know, one thing you could do is acknowledge that it isn't ideal, and you can, you know, say some solutions you would do after you solve the problem to mitigate that or make the design better. Let's look like. A test case we could not get a clear answer to was having 1, 0, 0, 1 on the left side, for example. I don't know what the exact structure of the tree is for that one. I don't know exactly what the tree looks like because it's kind of hard to know from text. Could you use BFS to solve the second question? You could. I think it would be much more complicated than a post-order traversal, but you can probably come up with a solution that uses BFS. It probably won't be as optimal as the post-order one, but I think you can. But definitely not as simple. Okay, let's see. Okay, let's see over here, minimum depth. Okay, let's see. One, let me just draw this out just so we're all clear. So we got 1, 0, null, 0, null, 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 1 is, oops. Is this what you were trying to say, Leonard? 1, 0, 0, null, 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 1. If this was your example, then we will not be able to, I believe you should not be able to prune this one. You cannot prune this subtree, you cannot prune this subtree, you cannot prune this subtree, and you cannot prune this subtree. Okay. Do you think binary tree balancing is a common interview question, or is that more of something that is a good idea to know conceptually? I never thought there might be a question about tree balancing, one question about it, but other than that, I don't think knowing how a tree balances itself is crucial to do tree problems. Again, 90% of the tree problems that you will encounter will just be your normal traversals or using an auxiliary data structure. So there might be a question or two about it, but it's not really a widespread common pattern or technique that you need to know to solve most binary tree problems. What is a good way to visualize recursive problems? In the beginning, recursion is, hard for a lot of people to get a grasp of, but I think it's actually really worth it to get good at recursion because a lot of these binary tree problems can be solved elegantly using recursion. So in the beginning, what you can do is, actually, here's one thing I want to show you guys. If you guys are having a hard time visualizing your Python code, what you can use is you can go to pythontutor.com and you can edit, you can paste, copy pasta your code in here, and you can run your code and you can see and visualize its execution, right? So you can kind of just step through your code and see what is happening. This, I think, really helps for recursion because, it kind of draws the recursive call stack for you. So that's, I think, just getting a hang of recursion. You can use this tool. When you are practicing, you should not rely on tools like these because they won't be available to you in an actual interview. So just use this to get a hang of it. But when you're practicing, try and do it manually because that's going to be what's expected of you in an actual interview. Is there a similar tool for Java? I am not sure. I'm sorry. If someone knows, go ahead and comment there. But I don't really teach with Java, so I'm not sure. Is the second problem something we can expect in an interview, or is it more on the easier side? I would say the second problem, I think, is fair game to get asked in an interview. I think if I had to, I guess, allocate the percentages of what type of difficulty question you'll get asked, is I would say 20% you might get asked an easy question, 60% you'll get asked a medium question, 20% you'll get asked a hard question. That's just based on my experience after doing a bunch of interviews. Oh, cool. They have Java. Thanks, Alexis. All right. Cool. Before you guys go, I am once again asking you to do the feedback survey. I know you guys have been getting this a lot, but this is the only way for us to iterate fast and make the class better for you guys as we go along. So please, before you leave, answer the survey. Again, it takes less than 3 minutes to answer. It really helps us out. But I have nothing else to give to talk about today. I will see you guys on Saturday. The mentors will be here, so that'll be fun. We'll talk more about binary trees. So before you go, please take our feedback survey. Also, I am here to stick around for about 10-15 minutes to answer any questions you might have about career or interviewing, or any questions you might have. I'll try my best to answer them. But after you finish the survey, feel free to leave. I will see you on Saturday. If you want to hang out, just stick around and chill, or ask a question if you have one.